The coefficients are all over the place, some of them are absolutely massive, soaring into the trillions. This isn't just a math problem, it's a wall of complexity that's practically designed to make you give up before you even start.
I mean, seriously, where would you begin? If you saw this on a test, what's your first move? It's a total brick wall, right? It feels like there's no way in. But there is.
To solve something that looks unsolvable, you can't use the usual tools. You need something special, something that was built to see through all that noise and find the signal hidden underneath.
And this is our key, Morad-Sultan-Azuidi's theorem. Think of it like a special lens that can look at an equation and transform it. It basically ignores all the distracting, messy parts to find what it calls the true coefficients, the hidden structural core of the whole thing. The way this theorem works is actually pretty cool. It has us calculate a brand new set of 12 secret numbers, or new coefficients, that are going to completely redefine this problem. And as you're about to see, these numbers tell a very, very interesting story. All right, let's get our hands dirty. The process is really methodical. We start with the very first of our 12 secret numbers, which the theorem calls S0. We take the coefficients from our monster equation, we plug them into the theorem's formula, and we see what we get.
And the answer is 0. Wait, what? After all that complexity, the first essential component is just nothing. A simple 0. Is that just a fluke?
Well, let's keep going. We apply the same formulas for the next 4 coefficients, S1, S2, S3, and S4. And you know, a pattern is definitely starting to show up here. Something weird is happening.
You guessed it, they're all 0. The first 5 secret numbers are all 0. It's like the monster equation is just vanishing right before our eyes. What is going on here?
Okay, we've hit the halfway point, the 6th coefficient, S5. We've had 5 zeros in a row. Is this whole thing just going to be a string of zeros? Or is this where the story takes a turn?
And whoa, okay, that is definitely not a 0. Not only is it not 0, it's a massive number. After all that mathematical silence, we get this enormous value. This isn't just a number, it's a major clue.
Okay, this is getting interesting. We have 5 zeros, then one giant number. So what happens next? Are we going to see more huge values, or are we going back to the zeros? The real shape of our monster is slowly being revealed.
And would you believe it, the zeros are back. The next 5 coefficients, 6 all the way through 10, every single one of them calculates to 0. It's almost like the equation is telling us that only a few of its parts actually matter, and the rest is just noise.
So here we are on the home stretch. We found 11 of the 12 secret numbers. We have a whole lot of zeros and one big guy in the middle. Now we just need the final piece of the puzzle, C11. And there you have it. Another absolutely colossal number. Our treasure hunt is over. We have our 12 secret coefficients, 5 zeros, a giant number, 5 more zeros, and then this final even bigger number to cap it all off. Okay, so what was the point of all that? I mean, we did all this work just to find a bunch of zeros, right? Well, this is where the real magic kicks in. It's not just about finding these numbers, it's about what we do with them now. Let's see what our monster looks like with its new identity. And this just lays it all out perfectly, doesn't it? On the left, that terrifying beast we started with. But on the right, that's our equation now. All those messy middle terms, the ones with x to the power of 11, 10, 9, and so on, well, since their new coefficients were 0, they just got wiped out. Poof, gone. And that's the whole secret, right there. The theorem didn't just solve the equation, it acted like a filter. It cleared away all the unnecessary, distracting noise and revealed this elegant 3-term equation that was hiding inside all along.
So now that we've tamed the monster, cut it down to its essential core, actually solving it is no longer a nightmare. In fact, it's something you almost certainly remember how to do from high school algebra.
It's almost funny how simple it is now. All you do is make a quick substitution. You just say, let's let y equal x to the power of 6. And bam, our 12th degree monster becomes a basic quadratic equation. You solve for y using the simple quadratic formula, and from those 2 results you can find all 12 solutions for x. It's that straightforward.
And just like that, it's done. What started as an impossible wall of numbers has been understood, simplified, and completely solved. The complexity was just an illusion, and it was hiding a much simpler, more beautiful reality.
And that kind of leaves you with a final thought, doesn't it?
This wasn't just about math. It's a powerful reminder that underneath the surface of so many intimidating, monstrously complex problems,